So hello everyone. I'm Paul Rouillet from Current Europe, the voice of innovative green technologies. And for this meeting, we're going to wait still a few minutes for people to join in, and we're going to start at 3:03. Would that works for you, the speakers?
Sure, that's good for me.
Okay, perfect. Let's wait 3 more minutes, and then we're going to start. Okay, so I think we can start, and people will join during the briefing. So first of all, hello everyone. Thanks a lot for joining us for this briefing. This is the third briefing of the. It's a series of 6 different briefing focusing on deploying innovation for DSOs. I am Paul Rouillet, a policy officer at Current Europe. And for those who don't know us, Current Europe is the voice of innovative green technologies in Europe, and our members are technology providers and manufacturers of technologies that optimize our current network. We are launching this series with a clear goal. It's to bridge the gap between high-level innovation and the practical deployment that our grid needs urgently. We all know that the energy transition is moving really fast. We're seeing a massive uptake of renewable that very often outstrip our physical infrastructure. So to meet this challenge, we must look beyond traditional reinforcement and start optimizing our existing network with market-ready, and this is very important, market-ready and fast technology. Today, we're diving in advanced conductors. We're thrilled to have Peter Hughes from CTC Global, Leo Richard from Epsilon Composite, and Dominic Quennell from Intertechnos with us to explore the perspective on advanced conductors. This kind of technology can transport significantly more electricity than conventional solution, offering an efficient and scalable approach to grid reinforcement. But before I hand over to today's presenter, 2 important points. The session is being recorded. So this is to ensure that we are building a library, resource library with other sessions. And also we will have time for Q&A at the end. So please note down your question as we go along the session. First, let me introduce today's speakers. So let me start with you, Peter. Peter, you joined CTC Global in 2016. You lead a team in developing ACCC business across Europe, and you promote advanced conductor technologies as a component in meeting energy transition objective. You also have been instrumental in rolling out CTC's new InfoCore composite core monitoring technology and other overhead line innovation. With a background in engineering and MBA, Peter, you have previously worked in defense projects, and you're also a specialist in logistic areas. You are currently based in Wiesbaden, Germany. This is a very impressive CV. Now, let me introduce you to Dominic Quennell. You're the co-founder and CEO of Enertechnos. Enertechnos is a UK-based electrotech company specialized in optimization of an electrical cabling system for distribution grid, but also for data centers, airports, and bidirectional wireless power transfer for charging electric vehicle. Enertechnos' principal technology is capacitive transfer system. We'll talk about that later during the session. It's an innovative cable design that delivers more power with less conductors over greater distance than what is possible with legacy cable. And last but not least, Leo Richard, you are an engineer from a Franco-British educational background with a versatile experience in complex composite structures. You supervised multiple industrial scale projects, and you currently act as an overhead line conductor technology expert for Epsilon Cable, a French company, and you're a designer, and the company is a designer and manufacturer of composite core used in advanced conductor design. Moving on to our today's agenda. As you can see in the first part of this session, we'll talk about overhead line conductors, first capability and operation, a summary of what it is, examples and use cases, and finally, also very important, safe installation practices. The second part will be dedicated to CTS, capacitive transfer system cables, with capability and operation, summaries and examples and use cases. And we will sum this up with best practices, best practice cost benefit analysis and key takeaways for DSOs. And then at the end, we will have 30 minutes for question and answers. So now I will leave the floor to Peter to present on the overhead line conductors. Peter, the floor is yours.
Thank you very much, Paul, and thank you for the introduction. Could you move on to the next slide, please? We are going to talk, as Paul said, about overhead line conductors and also CTS, advanced conductive cables. The two are grouped together. One works obviously overhead, the other underground. They both deliver the same capabilities. We're going to start with advanced overhead conductors. If I could have the next slide, please, Paul. Firstly, a little bit of history. Originally, transmission cables were all copper, but aluminium substituted that in the 1920s. And by the 1970s, permitting constraints really were more power was needed and permitting constraints. So it wasn't the case, as it had been previously, that you could put lines anywhere. Therefore, this concept of HTLS, which you'll hear a lot today, high tension, low sag, dear me, it'll come to me, high temperature, low sag, I apologize, like I don't know that, was steel cord variants in the 1970s through the 1980s and 90s, and various variants on that were introduced during those periods. And if you move it on a little bit, please, Paul. Just click once, thank you. By the 2000s were the introduction of two basic types of composite core. The first was a metal matrix core, which was really the first on the market. Then came a polymer matrix core pioneered by a couple of companies around the world. And really, these get put in the HTLS bucket, high temperature, low sag. Our argument is always, well, why do you want temperature on a network? Because it implies that you've got resistive losses. So these conductors, because of the nature of their design, put more aluminium around a core, and therefore increase the transmission capacity, and using different materials have lower resistive losses as well. So we like to classify them as high capacity low sag, although they very much fit in as a subset of HTLS, high temperature low sag. Can I have the next slide, please, Paul? So if you look at the picture on the left, you see a traditional conductor. 90+% of all overhead conductors look like this today and are installed like this. And on the right, it's a very different design concept. I don't know if you can see my mouse, and I'm not going to risk moving it around, but on the right, what we have is a polymer matrix core, which comprises thousands of carbon fibers surrounded by a glass fiber galvanic resistive outer layer, but also the construction of the conductor material is very different. Here you see on the left round wires, which all form part of the strength of the conductor system. And on the right, these are the trapezoidal wires made of soft annealed aluminium, which has a much higher transmission capacity from the get-go than the round wire solution. So you can add more material, which has less resistance, to deliver 2 times the transmission capacity for a given conductor diameter. Today on the market, there are a number of different design concepts around these, but they fall basically into this metal matrix core, primarily supplied by 3M in the US, and then polymer matrix core in various sizes or complexities, I would say, provided by a number of manufacturers. And so what we've put in this slide is the acronyms around these conductor types that are available today. These are categorized in the emerging DSO, TSO Technopedia as type 3 for metal matrix conductors and type 4 for polymer matrix conductors. The concept is the same, that the core does, above a certain temperature, the core does all the work in holding the system up. And because of the materials we choose for the actual transmission part, they're more efficient and they have the capability to run at very high temperatures. So I'd like you to move on to the next one, please, Paul, if you'd be kind enough. Right.
So
over to you, Leo. I'm sorry, I stole your thunder in the last one.
No worries.
I'm sure you do better.
No worries. I like the enthusiasm. Just a few questions before we head on, like we dive into this topic. In case probably some of you are users already of have heard about these technologies. So one first question for the audience, and feel free to write answers in the chat or speak out. If any of you have ideas why we would use these HTLS or advanced conductors, which is then another let's say naming convention for this technology. Any guess in the room before we address the question? And I'll just leave 30 seconds to if someone feels like speaking. Otherwise, I'll just go ahead. Okay, so let's aim at the answer then. There's actually a few answers, which we try to summarize on that slide. But basically, there are a few sweet spots where this technology is the most cost-effective in the market. Typically, in several applications nowadays in different markets in the world, different grids in the world, where we see problems with increased connection of renewables and issues with curtailment. So this type of technology, as Peter highlighted, they are very effective in reconductoring scenario primarily. You swap an old conductor for a new one, and you double the capacity of the existing corridor in a very limited time frame. It's very effective when you need to deliver more power, whether it's power that is produced, so when you increase, for instance, renewable generation, but also when it's power that is consumed. So consumption sites, such as the emergence of heavy data centers areas, also are prone to being connected with this type of technologies, which are very versatile. You can accommodate the peaks, the loads when the demand is at its peak, but you can also leverage onto increased benefits due to lower losses when the demands becomes more regular. It's applicable to any type of voltage. Typically, a lower limit would be about 11 kV. So distribution line would be from 11 kV to 90, 150, depending on conventions. And it's definitely very much applicable to transmission networks. So in transmission networks, it's applicable to any kind of high voltage, extra high voltage. We typically found the sweet spots for those technologies at let's say the upper level of distribution, sub-transmission levels, all the way to 150, 220 kV as well, would be a great example of the large amount of this product being deployed in the field. That was in terms of capability, but thanks to the properties of carbon fiber, we obtain conductors with enhanced mechanical performance. And that allows, for instance, very long spans that you found to river crossings, canyon crossings, lake crossings, for the, let's say, same capacity or double capacity of an existing conductor, because we have a very lightweight composite core that does not suffer thermal elongation. You have solutions that are very much suited to keeping low clearances for extra long crossings. Another application which is growing is the ability to mitigate wildfire with this technology, simply because they do not thermally sag. So it's also a consideration that a lot of users have, mainly, for instance, Western USA, Australia. So a few extra elements that Peter mentioned before, but the idea is that with these solutions, for same weight, same size compared to classic conductors, you basically have double the amount of ampacity. So that's very useful when you want to look at N-1 or peak usage, and lower resistive losses as well when you work at regular ampacity, let's say your baseline. So, but the both benefits are combined with the technology, as well as the ability to behave mechanically better than steel-based conductors. So all in all, these solutions are very effective in reconductoring scenarios, as I said, where you benefit from lower overall capex rather than building a new line. That's really the main idea behind this technology. Instead of building a new greenfield project, you can consider an existing line, upgrade it, and for a fraction of the cost and a fraction of the time, obtain a multiplying factor of the capacity you can deliver from point A to point B. These technologies have been around for 20 years, as Peter introduced, but they've been heavily tested, and we'll dive a little bit into this throughout the presentation. Now you can expect about 80, 90 years life expectancy as a minimum. So this is just a little bit of the work that has happened in the industry with manufacturers and users. But this product now reached a decent TRL level 9. It's been deployed in plenty of countries across the world in let's say extensive amounts, which means that it's completely compatible for any kind of distribution and transmission networks. I've concluded by speaking a little bit about deployment. Same here. If any of you have some guesses, I'd appreciate. But otherwise, as a guess, I thought it would be interesting to highlight which parts of Europe already have this kind of technologies operational in their grid, and we're not talking about pilots there. And on what level of voltage we found advanced conductors, Europe and worldwide. I'll jump straight to the answers then. So those are figures that are approximate but close to reality. Actually, next year it will already be more than this. But worldwide, these technologies are not anymore new technologies. They've been deployed extensively, and Europe is certainly doing its part with more and more deployments occurring every month. In Europe, most of the experience occurred in transmission networks, but more and more DSO are looking into it for different kind of applications. And it's applicable, as I said, to any kind of high voltage levels from 13 to, there's basically no upper limit. So at that stage, that usage has shown that it's a versatile solution, more and more use, simply because it's effective and it's effective, technically speaking, and cost effective as well. First, we'll then discuss a little bit about existing standards and test protocols for these technologies, as well as a summary of the benefits brought by advanced conductors for overhead lines. In terms of standards, there is currently two documentation, and this is maybe a bit more detailed compared to the overall focus of this workshop about general awareness. But if any of you are interested already into this type of technologies, I encourage your asset departments to have a look at this documentation. The first one, ASTM B987, is the oldest standard focused on this type of technology. It's been there for about 12 years now, and it's been adopted year by year on a global basis. It gives a decent amount of test protocols suited to evaluate the capability of composite materials to act as reinforcements for advanced conductors. So a very good reference, which was complemented in 2024 by an IEC standard that's then very much new. This documentation leverages the return of experience of the ASTM standard and brings additional test protocols that can be considered by utilities for further test protocols. So this is altogether, these two standards are the ones that have been used across the world on an extensive basis by different utilities as the baseline to build their own internal specification. And they're becoming more and more solid by the day because the usage is also spread. If we discuss a little bit about lead times or typical lead times compared to conventional solutions. So conventional solution in that example being a greenfield project. The greenfield project for new distribution or transmission line, we know that the main bottleneck is the construction time. How long from the point where I imagine my line to the moment where I can switch it on? Typically, that sits in between a few years to something like 10, 12 years, depending on networks and depending on the line, obviously. With the idea to use advanced conductors in reconductoring scenarios, you drastically reduce the permitting time. You still obviously have to get an outage and a permitting time to work on the line, but you get rid of any intervention required for that are typically associated with the construction of greenfield projects, such as environmental analysis, social analysis with the local population. So the period of time in between the onset of the project to the moment where installation starts, it's typically very short. We have experiences of projects from the genesis of the project to initiation occurring in 18 months. As a minimum, but in the installation time itself, very much similar to any kind of conventional conductor, Obviously, in a reconductoring scenario, you don't touch the towers, so you save time on the towers, but the stringing phase is very much similar. And a ballpark figure, an order of magnitude that you can keep in mind, it's that once we are in the deployment phase, about 10 to 20 route kilometer per month can be installed. I'll give it back to Peter for the next slides. You're muted, Peter.
Thank you. A commonly used principle across Europe that's applied, we've seen it in regulatory and policy, is this NOVA principle. I won't give you the German for this, but basically it's pretty logical, which is optimizing the current network before you do you undertake any tower work. So in years 0 to 1, almost immediately deployable are things that most of the audience will be familiar with: dynamic line rating, IMS systems, inertia monitoring, MPFC systems, and also digital twins to simulate the potential scenarios in the network. Where advanced conductors fit, and you will also see the term IGT, which we use as innovative grid technologies, but advanced conductors fit very much in this reconductoring space, which is probably about 90% of the projects in Europe, although we do have a number of new line projects currently ongoing. But this is the kind of where it started and where the sweet spot is in a quick reconductoring of a given line, which will double the transmission capacity. As Leo said, the permitting time, because you're doing almost a like-for-like replacement, is typically much lower. You don't have to strengthen the towers at all, so you use existing towers. Almost in never any tower foundation rework, so the projects are delivered much more quickly, and therefore very often we see that the overall project costs using advanced conductors compared to traditional conductor technology for a transmission increase are actually lower at the beginning. I think that's that for that. Could you move the slide on, Paul, please? Is this me? Yeah. So just some high-level takeaways on advanced conductors. Generally is very fast deployment, as Leo was saying, and you have this advantage of a baked-in capacity increase when you install this technology. They have a higher performance, lower resistive losses, and higher emergency capacity of any other conductor technology. Another very critical point is the lower sag that is achievable, and I see we have a question on that, which we'll address a little bit later. I mentioned the factor of potentially lower overall project costs. Conductors typically are between 15 and 25% of the overall project. So once you start to have foundation and civil works and tower strengthening, the costs escalate significantly. And another point that we would just like to get across is this is a very well-developed technology across Europe. We've had about 25,000 kilometers of the conductor installed and safely transmitting electricity today. May I have the next slide, please, Paul? So we're going to talk about a few use cases addressing those issues here. I'll very quickly run through these. If I could have the next slide, please. Again, use cases basically are doubling transmission capacity, network future-proofing, mitigating curtailments associated potentially with renewable energy injection into the network, improving clearance, and also application-related issues, for example, long span crossings and so on, which very much is where advanced conductors fit. Next slide, please. Starting off firstly in the Netherlands, which is a sub-transmission line, one of many, on their 110 kV network. As you can see from the photo on the left, the towers were very low on this, and they run over built up areas as well as fields. They're not far from the North Sea, so you can imagine there's a very heavy wind and sometimes ice loading on these lines. We used alloys to maximize the resistance to blowout, or minimize the blowout and ice-related sag, at the same time almost doubling the transmission capacity. And to address the question in the chat box, the sag reduction in this instance was minus 22% on the original conductor. Next slide, please. Thank you.
Oh, there I can probably jump in because it's one of our projects.
Yes.
So another typical example of using advanced conductors as a way to build in more capacity as the hardware, so not as a software-based solution, is future-proofing your grid with the embedded extra capacity. So that example here was performed 3 years ago in Montenegro on a 110 kV line. So what was looked at by the operator was the ability to reuse an existing corridor, an existing line that was about 6 years old with infrastructures that was aging, but as a way to keep the same nominal usage of the line, but add this extra capacity, since it's most likely that countries like Montenegro, that sits in the middle of the Balkans, will probably be an area where more and more solar farms are deployed. And by carefully selecting the conductor in this scenario, we could first build that new line, connected a local power plant to the capital, Podgorica, and having more capability embedded in an area where more and more solar panels are deployed, as a provision of let's say the capability that will increase in this area over the next 10 years.
Moving on to the next slide, this was a slightly higher voltage, but it was the only example I could quickly find, where the developer was mandated to increase the transmission capacity on a given line. Because it was a private investment, they did a cost-benefit analysis, which actually favored advanced conductors rather than any other available technologies. So the whole line was reconducted with advanced conductors, again quickly providing additional transmission capacity to take in renewable energy. So the capacity was increased by, as you can see, around about 40 to 50%, and a 20% sag reduction. Next slide, please. I'm sorry, I'm lazy not presenting this myself. Again, addressing this sag issue, we doubled the transmission capacity on this line, which was a 1332. I call it transdistribution because it was used both for main trunk transfer, but also as a distribution line. The sag difference is astonishing. And just please go and visit it. It's in a beautiful part of the world in Scotland, but as you can see, we reduced the sag from nearly 12 meters to just over 6 meters. And the arrows point to the legacy ACSR conductor, the red at the bottom, and then the blue one is the same phase using an advanced conductor, whilst more than doubling the transmission capacity. The next slide, please. And here's an example. I wanted to take one from Europe. Again, we're back in Montenegro, which is a long span crossing in Montenegro going to an island, Lake Skadar, crossing Lake Skadar. It was a 1.5 kilometer single span running between the towers. I've kind of inset the far tower and the near tower on the right hand side, and perfect application for advanced conductors, leveraging the low sag and increased transmission capacity for that tourist area. Next slide, please, and I think I'm handing over now. Moving on to safe installation of advanced conductors. Next slide, please, whoever's pressing the button. What the industry has developed over the years is a number of measures pre-installation and post-installation as well, intended to thoroughly brief the crews. We walk over the lines typically with the utility or the contractor to make sure that the conductor is able to be put in safely and provide recommendations. And we also provide active site supervision, some of which, a significant amount of which is free of charge as part of this service. And then we generally provide a post-installation summary. On the right is a reference, in fact, to CTC's website for a number of training videos to assist you in some background information on how to use the tools that we provide and how the system fits together. I won't go into detail on that now, but that's pretty comprehensive. And the next slide, please. So significant focus over the last few years has been on safely installing these conductors. Some utilities we know have concerns about breakages. They hear about this in the market. I want to emphasize that polymer matrix core, PMC core conductors have an enormous capacity for mishandling. And if I could have click again, please. And you'll see here two photos of one, a forklift compressing a tied up conductor, and a conductor being seriously bent. But next section, please. Our experience of the failures in the field have always been attributed to some form of mishandling of the conductor or overbending of the composite core. So we didn't just take it as all the supervision and training that we provided as being enough. From about 2020 onwards, next slide, please, we've introduced systems which monitor the integrity of the core before, during, and after installation. And I'm pleased to report that since we introduced this in 2020, about 8,000 kilometers have gone in of this type across Europe, and we have not had any installation related incidents when these technologies are deployed at the beginning. So it's a fantastic win, and it's really transformed many utilities' perception of risk associated with this technology. If you install this conductor properly, you won't have an installation. But if you have bad or rogue contractors and they don't follow the guidelines, this is your backup measure to ensure that the conductor has gone in properly. And We're going, Paul, if you'd like to take over, please. We're running a little bit behind time. I apologize for that.
Yes,
I've
I leave the floor
Sorry,
to
sorry, Dominic.
to work on to explain what is CTS advanced cable. Dominic, the floor is yours.
Thank you very much. Good afternoon, everybody. My name is Dominic Quennell, as per Paul's earlier introduction, and I'm the CEO of Technos. So first of all, a brief word about who we are and what we do. We're based in the UK, in the southwest side of London, and we have invented and we have patented a new form, an innovative cable for distribution systems, which we call capacitive transfer system. And in a minute, you'll see why. We have put in about 10 years of development work on this, and we have built up a library of test results from in-ground laboratory work and also work that we've done with various academic institutions over those 10 years, so that we can present that. And there will be opportunities to talk about that later. And moving on again, fundamentally, what the CTS is specifically, it's a cable. So at the moment, it's either underground or submarine, and it's designed for low, medium, high voltage in the range from 1 to 150 kilovolts. So this is not a transmission system cable, and it is AC, to be clear. It's not a superconductor. It runs at completely normal ambient temperature, and has been extensively tested in a wide range of temperatures. The objective that we have is that we can supply more power, we can send it further compared to conventional cable, and you'll see in the next slides the way that we actually achieved this. So the fundamental characteristics are lower AC parasitic losses, improved voltage regulation, and that gives us the opportunity to transmit at lower voltages, so that there's less transforming required, less transforming equipment required. We also have a reduced Ferranti effect, which in lower demand areas is very important. And finally, we can generate carbon offsets and create carbon credits because we can do this while using less conductor than you do with a conventional cable. The three broad areas that we have for the application of the technology are, first of all, at 50 and 60 hertz grids. Number one is electrical power distribution networks, DSOs, DNOs everywhere. Also, the export cables and array cables for wind farms as well as solar. And a more recent application is for data center campuses, where there may be a requirement to have some very localized generation to enable the data centers to function with a fairly minimal connection to the grid. Because as you'll all be aware, a data center's consumption of electrical energy is growing more or less exponentially. And last year in Ireland, it reached over 21% of all of the electricity generated on the island of Ireland was being consumed by data centers. And so this is something which is becoming very, very important. Another application is at 400 hertz, and this is for the fixed electrical ground power, which is required by aircraft when they're on the ground at airports. Typically, you have to have a dedicated line for the FEGP, fixed electrical ground power, running at 400 hertz, and those are very limited in length at the voltages that are required by the aircraft. So what we are looking at providing there is for a narrow body jet, about a 30 kVA supply. Wide bodies will have 2 of those, and A380 will have 4. And the limit you have on distance from the converter that's taking the power from 50 or 60 hertz to 400 to the aircraft is about 80 meters. With a CTS cable, we can build a whole 400 hertz microgrid, which enables that to be distributed much, much more effectively. The third and final application that we have, which is at a much higher frequency, 85 kilohertz, is wireless charging for electric vehicles. When we imagine EVs, we normally think about cars, but of course it also comes into maritime and also drones, airborne drones. So the difficulty there is compounded even above the 400 hertz level, because with a conventional wireless transfer system from the converter to the charge pad at 85 kilohertz, your limit of distance is approximately 6 or 7 meters. With a CTS version of that, and we'll come into this later, we can go up to 120 meters, which offers huge benefits in terms of cost. So moving on to the operating principle of the cable, in the top diagram that you see there, we have a conventional cable with the generation on the left-hand side, the load side on the right, and either a copper or aluminium conductor core, which is delivering as much of the power as possible. The lower diagram, and this is a representative one, the cable doesn't look like this, is how a CTS cable works. Because what you'll see there is that there is no galvanic connection between the generation side and the load side, but there's an inductive relationship. And for a lot of electrical engineers at first sight, this is quite counterintuitive, because you're always worrying about shunt capacitance. But when we contain that within the cable, we find, and we've proven, that we have a much more efficient level of distribution. So moving forwards to what a real one looks like. There are 3 of these diagrams. They are looking at grid cable layout at 50 or 60 hertz, first of all. If you look at the top right-hand picture, that is a cable that was made in a conventional factory on conventional equipment in Portugal, as a matter of fact. And the white material that you see there is a dielectric, which is keeping each layer separated from the other. And you'll also observe that there are 2 different colors there. They're all copper, actually. But for the purposes of this test, we had tinned copper, which looks like the more aluminium color. And so all of the tinned layers are connected at the generation side. All of the copper colored ones are connected at the load side. And between them, the dielectric maintains a complete insulation between layers, but there is the inductive transfer of power that runs through that. We're going to distribute these diagrams afterwards so that you can have a look in greater detail. But on the left-hand side there, you see how that whole cable is built up. 2 things I really want to emphasize here are, number one, that everything outside the conductor core is exactly the same as it would be on a conventional cable. So, and when we look at standards, that's something which is extremely important. And the other thing I want to emphasize is that this can be built in a conventional cable factory using conventional cable making equipment with very minimal adaptation. And our business model is to license the technology to cable manufacturers rather than being a manufacturer ourselves. So that was a very crucial part of our development. This is a smaller cable designed for the aviation sector. It looks very similar, but here we will make 3-phase cable. So it's a multi-layered CTS cable, all united in one 3-phase cable, which is what the aircraft sector requires. But again, in the upper photograph there on the right-hand side, you see the different layers of conductor, which are separated by a layer of dielectric and a semiconductor. When we move on to the 85 kilohertz, which is for the wireless EV charging sector, this is again quite a different looking cable, obviously much smaller because the power levels are much lower. and we have an out and return in the same conductor, where we've combined 4 conductors together. But each one of those is its own 2-layered CTS cable. And again, this has been made in a conventional factory. This one was made in the UK by a company called Concept Cables, and we've been testing this for 3 years and delivering power wirelessly between plates. So we have a long list of the data that we've collected on this, which we're very happy to share. So it's important to note as well that there are 3 components. It's not just a cable that have to be slightly different. So the cable itself, we've had produced in a number of different commercial factories in Europe, and also in Saudi Arabia. We have a licensee there in Riyadh Cables. The jointing is slightly different. This is a joint made by Lovink. Some of you will be familiar with that. And it's a standard off-the-shelf unit which has been adapted to joint the CTS cable, because in the joint we have to separate the 2 different layers of or groups of layers of cable, and ensure that there's no conductive relationship between them in the joint. The third part of it is the CTS protection and control system. At each end of the cable, situated either adjacent to or within the substation, there is a switching block which can be deployed deliberately to return the cable from being a capacitive transfer system to a conventional conductive transfer system, which you might want to do during periods of very, very low demand. But it also acts as a cable protection system, so that if there's a downstream event that's going to cause a sudden inrush current, which would be above the capability of the dielectric, we instantly switch the cable back so that it reverts to being a normal conductor, and then the conventional safety circuits within the substation will kick in and do what they're supposed to do. So the important consequence of that is that what the substation sees is a perfectly normal cable. It's not seeing something which is very different. And so that all of the normal control systems and safety circuits continue to apply. So looking briefly at the solution, what we're saying and what we're seeing here is that we have 10% lower losses typically than a conventional cable of the same cross-sectional area. We also see that with the same cross-sectional area, we can deliver 20% more power to the load than you can with a conventional cable with the same voltage drop. Now, that's something that we can prove repeatedly by using the circuit, the cable protection and mode selection device, because we can switch from conventional to capacitive to conventional to capacitive, and you can literally see the increase in power delivery through exactly the same conductor. We also note that we have a 20% reduction of system reactive power requirements, and that becomes very important where there are very strong inductive loads, which is increasingly a feature. And as I have mentioned, CTS cable of all kinds for all 3 applications is designed so that it can be manufactured using existing cable making equipment and at a competitive price. So broadly, a user, a customer of the cable factory can decide whether they want to minimize cost and say, well, we know that we don't need to increase capacity on this cable in this circuit in the foreseeable future, and so we can use 20% less conductor. Or you say, well, we can anticipate that there will be some increase in demand, which is more often the case, and so you install a CTS cable and give yourself the extra 20% of margin, but without having to buy additional copper or to upsize the cross-sectional area that you have in the cable. There's a number of operating advantages with CTS. The first one is obviously on cost reduction, both on CapEx and OpEx, because using lower voltages and simpler systems means that the maintenance costs are reduced, and we can also improve system safety. The second benefit that you will get as a grid operator with CTS is that you will have the self-compensating mode that gives you an extra tool. It's sometimes described as like having a sixth gear in your network management. Thirdly, and I've mentioned this just now, the reactive support. And so what we see with that is that the power factor is considerably improved compared to a conventional cable running under the same circumstances. Lower power losses is very important for any number of reasons, but we certainly see that we have much less voltage drop and therefore lower system power requirements. Just a word on power losses in transmission and distribution grids. In the UK, over the last 10 years, the average losses in transmission and distribution have been around about 27 terawatt hours per year. And that is slightly more than the total amount of power that can be produced by the new Hinkley Point power station, which is going to come on stream probably in the next 4 or 5 years at a cost of about £40 billion sterling. So there's a very material cost to losses. Now, we're not saying that we can eliminate them completely. Of course we can't. But if we can reduce the losses by 10%, that's a massive benefit. And again, if you look at it from the point of view on a global basis, the IEA, International Energy Agency, estimates that losses annually that are caused by T&D, or rather the carbon emissions caused by losses in T&D globally, are about a gigaton a year. And a gigaton is 20,000 Titanics every single year. So you can see that there's a very strong carbon and decarbonisation argument for reducing losses as much as possible. And the final point is on just general cost reduction by requiring less ancillary balancing equipment for injection of capacitance. Saves a great deal of money, both in terms of CapEx and in OpEx. So the way that we approach this is, and I'm conscious of time, I won't go on for too long, as a holistic solution. So we look at the whole design that's required to deliver the power and taking into account likely future demands, and that gets adapted in cooperation with the DSO. So just a very quick summary on the standards to keep ahead of time. We are compatible with all of the regular cable standards which are listed there. They'll be familiar to most of you. And in certain cases, we do some additional standards compliance testing where there are capacitive or capacitors for power systems have their own standards, and we meet both. So we meet the cable standards and we meet the capacitor standards, just so that we are totally secure, and moreover, so are the users and operators of the cable. Again, I'm conscious of time, and this is a busy slide, but the grid applications at 50 and 60 hertz are very important. And what we are seeing as demand drivers for change is the requirement for increased power capacity and reduced losses at a time of rising energy demand. And this is something which is difficult to provide with a standard, a regular conventional cable. So the solution here is for a different kind of cable which has lower losses, uses less conductor, and can travel over longer distance. Second application is really important. I'm not going into airports in too much time today because we don't have a lot of time. But the wireless charging application is super important for grids, and I'll tell you why. By using wireless charging, the traction batteries in the vehicles can become used as a distributed energy storage asset much more easily, because if you're parked over a charging pad in a wireless equipped vehicle, you are already engaged in the grid in a bi-directional way, so that power can be transferred from grid into the traction battery or borrowed back from the traction battery at times of peak need. And the way that we do this with CTS is around about 45% of the cost of doing it with a conventional alternative wireless charging system. In terms of efficiency, wireless charging is now at parity with plug-in charging at the AC level. So we are typically achieving somewhere between 90 and 91%. The range that you'll see with a normal plug-in charger at AC is somewhere between 85 and 92. So we're right up at the top of that range. A very vivid application, which we're proud of because it's right across the road from the office in which I'm sitting now, is the UK Royal Mail. And we do this through our subsidiary, which is called Electric Green. The opportunity that they have there is to earn money from selling power back to the grid. And the way that that works is they have an installation of 10 charge pads. They're using Peugeot vans made by Stellantis, which are wireless equipped. The first one has been done. We have more which are in the production phase at the moment. But the crucial thing there is that they have 38,000 vehicles in their fleet spread over 1,200 depots. And as a consumer of power, obviously that costs them a huge amount of money. But when they can sell power back into the grid, there are two benefits. They can earn up to estimated £14 million per annum. But second, it means that at times of peak load, they can lend power back to the grid, and they can prevent additional, perhaps gas-powered power station from being turned on. So there's a very, very strong benefit there on both sides. So moving on to the key takeaways of this technology. Number one is we deliver more power through less conductor over greater distances. Second, we have international patents, over 12 different patent families relating to this, bearing in mind that our business model is licensing the technology. The licensing model means that DSOs, DNOs can continue to use their preferred suppliers. That there's nothing that gets in the way of any cable manufacturer having a license from us. We have tested in-ground in the UK over many years, and the results of this will be presented fairly soon. And we have this broad range of applications from grids, from data centers, airport FEGP, bidirectional power transfer at vehicle to grid level for electric vehicles. So I think now I'm going to hand back to Leo for the best practice on the cost benefit analysis.
Leo, moving on to the next slide, maybe there's a part, maybe Dominic, where you can explain the mitigating network constraint for and the recommended CVA approach for that.
I'm sorry. Yes. Let me just do that. So I'll hand it to Leo after that. So basically, the mitigation of network constraints, when we're looking at the cost benefit analysis, is how does this help over a period of time, taking into account the length of time that a cable is typically going to be installed, which is, the normal target is somewhere in the 45 to 50 year range. And so we have lower losses, there is more power delivered to load. So there's going to be lower OPEX behind that. The second benefit that we have to mitigate the constraints is the use of less conductor to deliver a given amount of power. With copper prices in particular going up the way that they've been going and are forecast to continue to rise, the lower capex there becomes extremely important. And then finally, the CTS can go at a greater distance with lower voltage, at lower voltage. And so there's less requirement for the transformer equipment, which gives you a benefit both in terms of capex and opex. So when you take all of those together into the cost benefit analysis, the use case for this kind of cable becomes very compelling indeed.
So I'll continue speaking now for mostly for advanced conductors used in overhead lines application. Similarly, when you are building a CBA, you want to have more of a TOTEX approach, since most of the existing other solution have much higher operational expenditures that in turns affects how the CBA analysis is performed. So in order to properly do a CBA to value the possibilities of advanced conductors, you first need to keep in mind that you can achieve much faster deployment, and in turns there are different ways to consider this in the CBA. We have written a series of papers for CIRET 25 edition, so I encourage you to have a look at this on they are available on current website for further information, but just a few examples here. We mentioned before that the reduction of permitting obviously is something that you want to consider into the CBA analysis. For anything related to handling, as we are much similar to conventional conductor, there is no further reduction here on the cost induced when you are in the field deploying the technology. But typically, something that is very valuable and that needs to be leveraged into a cost-benefit analysis is the amount of energy you saved when considering the structures. The fact that you most likely do not have to refurbish the towers, you can consider existing assets, definitely yields important savings. So a global total cost of ownership approach allows you to consider that simply having a little bit of a deployment of advanced conductors and considering the input of losses that you save over time very fast repays the investments. We are talking about a couple of years here. 1 to 5 years usually are enough in terms of loss savings to repay the upgrade. Not even accounting for the fact that by doing so and by properly dimensioning your conductor system, you can have a built-in capacity, as we highlighted as well, which in turn in the future will be used to future-proof the network. As a personal example, for instance, I know that some distribution companies in Australia are heavily relying on this approach. In this country they installed insane amounts of capacity, production capacity in the middle of the desert, and this consideration they are already facing because they are forced to upgrade lines that they have installed already a couple of years before, since they are already maxing out. So that approach is further beneficial for the CBA. We'll just conclude on that part with a small schematic here. You'll have these slides available so you can have a further look at it. But the idea behind this was to present a graphic vision on how both deployment time and savings can be achieved by going for an advanced conductor systems. So in that example here, you see some of the elements we've already mentioned. A typical conventional solution in red, lead time from project genesis to energization at year 0. And we oppose that to, in green, an advanced conductor project, which what happened? Paul, did you do something? Oh, it's Dominic that still has the hand. Sorry, I'm going to take the hand, Dominic. Okay. So in green advanced conductor solution, showing that within the time span of one traditional solution project, greenfield, you can achieve 2, 3, 4 equivalent reconductoring projects. Those are order of magnitudes, which are actually close to the reality, and they are associated with savings, because we've explained that even in terms of capex, if you consider just a new build versus an upgrade of the system, the amount of money that needs to be injected into the upgrade is much smaller. We will just conclude on this last slide, really that the key takeaways, the key benefits that the solutions that the three of us presented today, whether it's for overhead line or cable solutions, when you, as a utility, you are looking into that direction, first, the best way to go at it is to look at a global cost analysis as per the CBA example I just presented. The speed of deployment is also one of the key reasons why these technologies are more and more used. We live in an era where fast upgrade is the key, and these solutions are especially suited to deliver power faster to the consumer. Losses is also inherently a big part of these advanced conductor systems. Unfortunately, not considered enough, not leveraged enough at the conception level of a new project. But should this happen, most of the product installed nowadays in the world would rely on these type of technologies. Future-proofing is also something that we mentioned a couple of times, and very importantly, especially looking at the future of the electrification of Europe, these components, if taken into account properly at the genesis of a project, also leans in the direction of having more capacity hardware directly built in the system. And last but not least, as per the CBA example I just presented, both the solutions enable lower TCO, which for both the utility and the end user is a win-win scenario, ensuring the proper tools are deployed at the CBA analysis to value these technologies as a solution for networks. All right. Thanks, everyone. Paul, you want to conclude?
Yeah, of course. Thank you. First of all, thank you so much for the presentation, Peter, Leo, and Dominic. It was very interesting and thoughtful. There is a lot. There was a lot. So now it's time for the Q&A session. So if you have any question, you can ask it in the chat, or you can ask directly here. I saw that there was some question from Mark Norton in the chat. So maybe Mark, you want to directly ask your question here. Okay, so I can ask the question that were in the chat. So let me find them. So first question, Mark Norton. Oh, sorry. Can you mute your microphone, the audience? Okay, thank you. So Mark was asking, what is the typical difference in SAG from an advanced conductor to a conventional solution in meters or feet? It was based on the picture that was presented at the beginning. So if one of you, maybe Peter or Leo, you want to answer that question.
Yep, I'm happy to take that one. That actually referred to one of the application slides. So we were reducing the SAG by about 50% on that particular project. But what is worth mentioning is that the SAG reduction is really dependent on the profile of the the conductor that you're putting in, and also the the modulus of the core itself. So it's not, you can't say it's a direct comparison. We tend to offer two alternatives to our clients. One is to maximum sag mitigation, and the second is maximum capacity. But in all cases, because of the design of the composite core, you will always have a sag reduction over a traditional steel core technology.
Thank you for that answer. Now I have another question from Mark Norton, maybe to you, Dominic. Is asking in the chat, it would seem that CTS technology is a clever innovation to existing material and construction techniques, which means that any risk of technological development is limited. Has your experience been that the system operators and asset owner recognize this?
Thanks for relaying the question, Paul. The answer is that it is indeed a clever innovation, and the important thing that we are always telling people is that the very worst case scenario that you're going to get with a CTS cable is that there is some form of dielectric failure, at which point it reverts to being a conventional cable. So there is an inherent protection in there anyway. That said, and I know that there are lots of people from DSOs, DNOs on the call, there is a reluctance to be the first to deploy the new technology or any new technology. And we are now working with one of the UK DNOs on very detailed planning for what will be the first in-grid installation of the CTS cable. And that is going to be approximately 15 kilometers. It's going to be actually bringing the power in from a wind farm, onshore wind farm that has been repowered, where there's naturally an increase in the power to be transmitted through the cable, and it runs through an area where they have to use cable rather than overhead line. So that is now in planning, and there will be more news on that later on this year, probably by the end of I would say the middle to end of June. But it is always the difficulty with innovative technologies that there is, it's an inherently conservative industry. We understand the reasons for that, but I would say that sometimes there is no alternative to innovation to deliver the capacity reliably that is required in today's world. People have to accept the innovation, and in particular with us, where we mitigate the risk to such a huge extent that it's barely noticeable.
Yeah, thank you so much for that answer. I maybe asking just a small follow-up question. You mentioned that we're gonna hear more about it next, so maybe you can clarify on this. Are you going to present something soon, or?
Yes, we are. We ran a project for the UK government testing cable over a period of about 2.5 years on some private land that we rented in the southwest of England, and that was sponsored by the UK Net Zero Technology Centre. And we've collated all of the results of that, and that's been accepted as a paper that will be presented at the SARED conference in June in Brussels this year. So that will be an opportunity for anybody to see what the outcome of that trial was. It passed with flying colours as far as the UK government, the Net Zero Technology Centre was concerned. It proved exactly what they wanted to see in terms of the improvement in performance, and the fundamental outcome of that really was that we could repeatedly show that we're delivering in the order of 20% more power through the cable when it's running as a CTS cable than when we run the same cable, the same conductor in a conventional way. So that's June, SARED, Brussels. Please be there.
Wonderful, wonderful news. I'm sure there are people in the audience that will be present. I think Current will also be there. Let's we'll see at Siret. Maybe one last question to you, Leo or Peter. At the beginning of the slides, you mentioned that the overhead line that you present at TRL 9 level. And I was wondering how you can justify this level of TRL.
It's a good question, Paul. Thank you. And we have seen in some European publications and technical articles that overhead advanced conductors are considered as TRL 7 to 8. But I think our argument is always TRL 9 is that it's serially deployed, and that ticks the box for overhead advanced conductors. We have, as you saw, I think Leo showed in an earlier slide, over 25,000 kilometers of these conductors silently delivering power, and they have been for getting on for 20 years now on European networks. So that's a TRL figure we would challenge, and we would say always that this is a ready solution to be deployed quickly to increase transmission capacity. So thank you for that.
You're welcome. That's a very interesting topic, because we've heard also from previous presentation that there was also some issue with the TRL level, and that a lot of the technologies that we're presenting during the DSO innovation briefing are already deployed. They are already having an impact on the grid in Europe. So. This is nice to hear. Now to conclude this session, thanks again the speakers Peter, Leo, and Dominic for the presentation, and thank you the audience for being here. Feel free to reach out to us if you have any question, either now or later by email. If you have any comments on the series. On this session in this session in particular, or on the series, that would be appreciated. It's a design tool for DSOs, so it would be really good to have feedback from you. So please let us know. We will of course keep you updated on the series, and if there are new sessions. The next one is the 27th of May. It's on voltage regulators. So yeah, we will discuss voltage regulator next time. Thank you for your time, and I wish you a pleasant day ahead.
Thank you, Paul, for the moderation.
Welcome. Goodbye.
Bye-bye.
Thank you, everyone.
Thanks, everybody.
Good day.
Bye.